In this section, you will study the GMRES, Generalized Minimum Residuals. The GMRES can be used for solving linear systems AX equals B with arbitrary non-singular square matrices A. The application of the classical iterative solvers, such as relaxation methods and the conjugate gradient method, was limited to either diagonally dominant or symmetric posit-definite systems. For this general solver, GMRES, the essential ingredient is Arnoldi iteration. The Arnoldi method will be applicable for both linear systems and eigenvalue problems. Let's consider a matrix decomposition in the form of similarity transformations as in this equation. A is QHQ transpose. Here Q is an orthogonal metric, which means Q transpose Q is identity, and H is an upper Hessenberg metric. The upper Hessenberg metric has this form. It's upper triangular metric with one more diagonal just below the main diagonal. These entries are non-zero, and everywhere is 0. Then the metric is an upper Hessenberg metric. For this similarity transformation, the Arnoldi method uses a modified Gram-Schmidt process. It is less stable than the household reflectors. However, it is the advantage that we can get columns of Q one at a time. Let's see a derivation of Arnoldi iteration. We start with the similarity transformation. A is QHQ transpose. By multiplying Q right side in both terms, then this will become AQ and that will become QH. In detail, this equation can be written in this way. AQ, and that is Q and H. This is an upper Hessenberg metric. Now, rather than this whole system, we consider only part of this system. For k less than n, we define qk, collecting only k columns of q. Then qk plus 1 will have q plus 1 columns of q. And h tilde k is defined. It is not a square metric. It's k columns and k plus 1 rows. With this definition, we can easily verify a qk is qk plus 1 h tilde k. Quite easy to verify. Now, assume we are recursively construct columns of Q and columns of H, so that in the following we'll see how to get the last columns of H tilde K and QK plus 1. That means this coefficient, these values, and QK plus 1. The recursive computation of the columns of Q here given in this equation is known as the Arnoldi iteration. let's try to construct and get the last columns of H and Q. Okay. Now, if we consider AQK and then the last component, last column, then A times QK, that is the last column, that must be, now also here the last column, that must be now that one times this one, so that is exactly this one, along with Q1, the coefficient is H1K, now H2K, Q2, H3K, Q3, and so on. So we have that right side. Okay. What we have to get is to get QK plus 1, and of course this coefficient. So we move this one to left-hand side and divide by HK plus 1K to get QK plus 1. Okay, that's the equation. And this is a form of modified Gram-Schmidt process. Now we have to decide these values and the bottom. Okay, we can do it easily. In order to get these values appearing on the top of this equation, we may try to multiply Qj in the dot product, Qj dot AQ. Then these are Q1, Q2, Q3. These vectors are orthogonal each other. So only jth one will remain there. So the jth one will be HJK and now QJ. So once you try to get QJ dot product, then this dot product will be 1 and the remainder part is HJK. That is exactly this one. So by multiplying the dot product from Q1 up to QK, you can decide this all quotients. Okay, so we got them. And then now remainder part is to decide this one. Here the requirement is, okay, this is a vector. Now QK plus 1 must have length 1 so that we measure the norm of this vector and assign it to for the quantity. Then eventually QK plus 1 has a length 1. So here we have HK plus 1K is the norm of this top portion. Then eventually QK plus 1 will have length 1. So we finished the computation of these terms, and now we found the new vector in QK plus 1, right? Okay. In this way, recursively, we try to construct HK and QK plus 1 so that we can finish the computation. Okay. Now we have the first step of the Arnoldi iteration. We start with arbitrary normalized vector Q1. Then, if we are using this formula, then Q2 is AQ1 minus H11 Q1 divided by H21. So there is this formula. And we apply dot product along with Q1. Then that will be left-hand side will be 0. And then here AQ1 here minus H11 Q1 dot Q1. This will be 1. So we recheck this one. So here H11 is this quantity. Now we measure the norm of this top portion to get H21. Then Q2 will have length 1. Quite easy. So each time, recursively, we try to get these coefficients for H, and then we try to construct a new Q vector. So keep going. This method is called Arnoldi iteration. Here we summarize the method. Start with arbitrary non-zero vector and normalize to become Q1. And then this is Coulomb-Schmidt process. And then for the remainder, we, of course, during the time, we can get the quantities for H and then measure the length for the remainder vector. And that is HK plus 1K. Now normalize the vector V to get new column in QK plus 1. That's the Arnold iteration. Okay. Now let's go to the derivation of the GMRES method. The main idea of the method is to solve a least squares problem at each step of the iteration. For the new iterate, we try to get it so that the new iterate is minimizing this residual. Now, X is chosen over the kth order Kirchhoff subspace spanned by B, AB, and AK, H to K minus 1B. These are K vectors spanned by these vectors. And among every possible X in the space, we try to get the vector minimizing this residual. Each iteration, we try to solve this minimization problem. So once you try to implement in this way, then that is quite expensive. But we'll try to use some mathematical identities, and then also we'll try to use something else, and then we can get really quite efficient algorithm. Let's go step by step. Okay. Now, and we consider a matrix that's called the Kirchhoff's matrix, collecting this the basis vectors. Okay, this by collecting these vectors, we name it the Kirchhoff matrix. Of course, it's kth Kirchhoff's matrix. Then, once we've found xk, then that must be now linear combination of these columns, because it must be inside the space. So these are columns. So the linear combination of this column can be written in this way, along with the coefficients c, and xk must be given in this way. So rather than ax minus b, we may write in this way. So we try to minimize now over c, along with ax, akk, c minus b. So these two problems are the same, but it looks more here solvable. However, this one is really too expensive. We can solve this problem by using, for example, QR factorization, and however, it's expensive. Also, the algorithm is not so stable. So we need more simplification. rather than using this basis, this metric, we may try to use the basis from the Arnoldi iteration. So it's another approach to solve that problem. In fact, we are trying to solve this one, but if we try to do it conventionally, then it's not stable, and also it can be expensive. So now we try to choose an orthogonal basis for the curl subspace Q1 to Qk. These vectors can be found in the Arnoldi iteration. Okay, then now this collection is Qk. So the xk, once we found the kth iterate xk, then it can be written as the metric Qk times y for some y, because xk must be in the space spanned by these vectors. So that once we consider the metric, then xk must be the metric with a coefficients vector. So now the problem is changed into this form. For xk, we are using qky. Now we try to minimize over y. So we have to solve that one. Yet, this one is not easy to solve. It's better than earlier this method, this minimization. However, it is yet expensive. So we'll try to use the partial similarity transformation. We already know that AQK is the same as QK plus 1 H tilde K. So AQK, this portion, is now changed by Q, K plus 1, and H tilde K. Okay. Then Qk plus 1 has norm-preserving property. Q is an orthogonal metric, but if you collect only K plus 1 columns, yet it is satisfying this property. That means that once Q has norm-preserving property, then Qx for any vector, Qx norm is the same as x norm. After application, you can get the norm is not changed. You can check this one quite easily. For example, square. Then Qx transpose, this term, the square term is the same as that one. Now we rewrite this one in this way, x transpose q transpose qx. This is identity, so that is x transpose x, which is same as that, right? So for orthogonal matrices, and also there, the columns, and having this property, always these matrices are preserving norms. Because of that, here Qk plus 1, we multiply its transpose to become identity, and appear here Qk plus 1 transpose. So we reach at this minimization problem. Now, it's yet a bit complicated. Final simplification is done along with that one. Now, this one is norm over B times E1. E1 is the first component is 1. Below every the value is 0. This is the unit vector in the first coordinate direction. So it becomes, eventually, it becomes a constant vector. And the first component is normal BB, and every else is 0. And now minimization of this problem is very easy. And this is an Hessenberg metric, and you can solve this problem quite easily. It's really much simpler, and also you can use very efficient solution method for solving this one. Now, we'll see first why this one and this one is the same. Okay, let's see this example. Qk plus 1 transpose B is now B norm E1. Okay, Qk plus 1 transpose B can be written in this way. Now, if we start with the collapsed subspace with B and A, and B and AB, and so on, then Q1 start with the B, and Q1 is a normalized vector from B, so that this one is basically, okay, if we are using this one, then this top one is the same as now B over B norm, and that B, so that is same as B norm. Now from second one, and Q2 is normal to now B, because in normal to each other. Q1 is orthogonal to Q2, and everywhere over there, everything is in orthogonal each other. But Q1, okay, Q2, the Q1 is a scaled B, which means that, again, this dot product must be 0. So everywhere, except this one, everywhere it'll become 0 and 0 over there. So we have here Q transpose K plus 1 B as B norm E1. Okay. So we can summarize the method. Q1 is B over V norm, and we perform the step K of Arnoldi iteration. In each iteration of the GMRES, we have to do one more step of the Arnoldi iteration, so that we can compute the new entries for H tilde K and QK, and we try to minimize this norm over Y by using QR factorization. You can do that, and also you can do this one quite effectively. This one, as K increases, it includes only one more column, so that once you can keep the previous solution, the detail of the solution, then in the next step, you can use it, so that only extra part can be done to get this solution. If you can do, then here it'll be really efficient. You can do this one quite easily. After getting Y, now QK is multiplied to get new iterate. That's GMRES. Now it can be implemented in this way. Now this implementation is with arbitrary initial guess. Sometimes here you may get really good approximation for X, so the X0 can be good approximation. Then now here Q1 is from residual, normalized residual for X0. So it is almost same, but you have to put always this one for arbitrary initialization. Once you start with x0, s0, for example, x0 is 0, then R must be B. That means that Q1 is now B, and oops, okay, that is B over the norm of B. Okay, so that is exactly the mathematics we did earlier. But now for some non-zero initialization, you can begin in this way, but in each iteration you have to add x0 at the end of over there so that you can get new iterate. That is another form of a GMRES implementation. Now in Python, I made a program, and here I'm following exactly this new form, and here at the end x0 is added, and here I try to save each iterate, and at the last moment change it into the NumPy array form, and now here I try to print out. Okay, there's a metric, 2x2 metric, and now right side is 32, and x0 is 0, 0, so that this portion has nothing. There's no effect. However, anyway, this is a new form of implementation. Now I start with 0, 0, and after 10 iteration, and I try to get the iterates. Okay, let's see here. The output is, okay, that's initialization. And then after 10 iteration, we reach this one. The true solution is 2 and 1. And so it is approaching to the 2 and 1. Is slower for this example, quite slow. And you may think that it's slower than so conjugate gradient method or some relaxation method such as the SOR. However, this one is working for very general matrices. But for relaxation method, it is working well for diagonally dominant matrices. For conjugate gradient method, is for positive, symmetric positive definite matrices. But this one is for general algebraic systems. Of course, for the GMRES, there are many techniques for preconditioning, so you can accelerate the convergence. You can enjoy very good convergence when you can find a good metric such that your algebraic system is well preconditioned. As we already learned how to get preconditioning, and we study conjugate gradient method. Okay. GMRES is implemented in various software packages. For example, in MathTalent, you can find it, GMRES, and in Python, it's a SciPy, and among sparse matrices, and linear algebra package has GMRES. So you can use it. Okay, that's the end of section and end of chapter. Thank you.